Okay, welcome to the third video in the penicillin series. This one is about amoxiclav, but first let's just go back and review the summary points about amoxicillin and ampicillin before we move forward. 1. Like penicillin G and V, they cover streps well. 2. They have some extended gram-negative coverage over pen G and V, including some strains of E. coli, H. flu, and Proteus mirabilis. 3, they do not cover most other gram-negatives. 4, they do not cover Staph aureus. And 5, they are the best option for Enterococcus and Listeria. Great. And here are your new summary points for amoxiclav that you're about to learn all about. 1. Many bacteria, particularly gram-negatives, can have resistance to beta-lactams by producing beta-lactamase enzymes. 2. Amoxicillin clavulanate has a beta-lactamase inhibitor that extends its gram-negative coverage, including beta-lactamase producing organisms, such as E. coli, Proteus, Klebsiella, and many other enterobacteriaceae, your gut gram-negatives. The nasty anaerobes, Bacteroides, Fusobacterium, and Prevotella. Hemophilus influenza and Moraxella catarrhalis, which are respiratory tract gram-negatives, and Capnocytophaga, which we see in dog bites. Okay, so I want to start by talking about bacterial mechanisms of resistance, and let's use a good old war analogy here. So here's the bacterial cell membrane with its peptidoglycan layer on the outside and the bacterial cytoplasm on the inside. So the bacteria is like a medieval city that's trying to defend itself, and the penicillin binding proteins are the gates. So we are the ones that are trying to destroy the city by sending out soldiers with battering rams to break through those penicillin binding protein gates. Okay, so one of the first lines of defense that a gram-negative uses is by building an outer barricade, which we've talked about. But sometimes that's not enough. We can train new soldiers that know how to break through that barricade and get to the penicillin binding proteins, or the gates. Another way that bacteria can defend itself, though, is by sending out soldiers of their own into battle, and these are called beta-lactamase enzymes. So these are enzymes that bind to and inactivate the beta-lactam ring, rendering the antibiotic ineffective. They can be secreted out of the cell, like soldiers sent out into the battlefield, or they can exist in the periplasmic space, like archers that are mounted on the walls. The DNA encoding the beta-lactamase enzyme, which is kind of like the army commander or general, can either be chromosomal, meaning they're intrinsic to the bug, so it's like a commander that's from that city, or they can be plasmid mediated, which means DNA that's shared among different organisms on mobile elements. And this is like a commander that's, from a nearby allied city. There are other types of resistance mechanisms that we'll talk about in the future. So a quick note about stewardship. When we are giving antibiotics, we are enabling proliferation of strains of bacteria that have either these chromosomal or plasmid-mediated resistance genes. And these plasmid-mediated ones are especially concerning because they are on mobile elements, meaning they're allowed to be transferred between different species of bacteria. And this is how bacterial resistance can spread among different species and even among different hosts at a population level. So let's keep learning about antibiotics so we can choose wisely and not contribute to this problem. Okay, so back to actually talking about beta-lactamases. Not all beta-lactamases are created equal. They're sorted into these different classes. But I don't want to get too much in the weeds about this. I want to focus your attention on the class A, TEM, and SHIV. These are the more common regular beta-lactamases, we'll call them. They can degrade penicillin G and V, AMP and Amox, and sometimes first-generation cephalosporins. But third-generation cephalosporins still work against bacteria that produce these TEM and SHIV beta-lactamases. So remember when I told you that ampicillin covered some additional gram-negatives over penicillin, i.e. some strains of E. coli, H. flu, and Proteus? Well, most of the strains that it doesn't cover are the ones that produce these TEM and SHIV beta-lactamases. But we can overcome this with a beta-lactamase inhibitor like clavulanic acid. Back to the battlefield. So this is basically an arms race. To compete with the beta-lactamase, you can pair your penicillin with a beta-lactamase inhibitor that inhibits the beta-lactamase. So amoxicillin we pair with clavulanic acid, that's amoxiclav. Ampicillin we pair with sulbactam, that's amp-sulbactam, which we don't have in our hospital. So basically what we're doing here is you're sending in your specialty infantry to defend the battering rams.
Choose your
antibiotic
carefully, Leonidas.
may not cover beta-lactamase producing Hemophilus influenza.
This is
Amoxicillin. Okay, so let's talk clinically. When you add clavulanic acid to amoxicillin, you extend its coverage to more gram-negatives that produce these beta-lactamases. So that means more strains of E. coli and proteus. And also klebsiella, which remember I told you intrinsically produces beta-lactamase. Amoxicillin is also great for covering what I like to call the nasty anaerobes. So Bacteroides fragilis, Prevotella, Fusobacterium. These are the bad anaerobes that can produce beta-lactamase, hence you need the clavulin. So, the enterobacteriaceae like E. coli, klebsiella, proteus, these nasty anaerobes, all of these live in the gut commonly. So, we see amoxicillin as a really good option for intra-abdominal infections. Acute appendicitis complicated by an abscess is a great example. This is a situation where sometimes you can't always get drainage and you don't always know exactly what you're treating. So you have to think, what bugs could these be? Well, they're bugs that come from the gut. And actually the most common organisms in acute appendicitis are Streptococcus aeruginosus, E. coli, and Bacteroides fragilis. So amoxicillin clavulin is a great option to cover those three bugs. This is why you often see oral amoxicillin as our step-down option at the end of that therapy. See how this stuff can actually make sense? But really, it's all about needing to think about the bacteria to understand why. So, that takes time, but stick with me and we'll get through it, I promise. Amoxicillin will also allow you to cover more strains of H. flu that might be beta-lactamase positive. So, for example, if you had a complicated sinusitis with an abscess, or with an orbital cellulitis. Typically, you see second or third generation cephalosporins, but you could use an IV amoxicillin in this case. Either way, it's often also our oral step-down agent in this context. Amoxicillin also reintroduces some Staph aureus coverage. So remember, Staph aureus produces a penicillinase, and that's why AMP doesn't work. But that's a beta-lactamase, so the clavulin component helps with that. But it's still not your best anti-staphylococcal option. Remember, cloxacillin and cefazolin/Keflex are the best ones. But you still can be reassured that you have reasonable Staph aureus coverage with amoxicillin. Here's another one, Moraxella catarrhalis. So this is a bug that I deliberately didn't tell you about before. It's a gram-negative and also a colonizer of the upper respiratory tract, just like Hemophilus influenza. So it can cause acute otitis media and acute sinusitis, but not as commonly as strep pneumo and H. flu. You can't cover Moraxella with AMP or Amox because it near universally produces beta-lactamase, which is why we would use amoxicillin if we thought we needed to cover this bug. So this explains what you may have seen in the acute otitis media CPS statement. Here it is. It may be prudent to use amoxicillin if the child has had a recent treatment with amoxicillin within the past 30 days. This is because that suggests the failure of AMP or Amox might have been due to a beta-lactamase producing H. flu or Moraxella catarrhalis. Another one, in the setting of acute otitis media with purulent conjunctivitis, which is called otitis conjunctivitis syndrome, H. flu or M. catarrhalis are more common to cause that syndrome, and therefore treatment with amoxicillin in that case is recommended. Okay, last one, I promise. So what about giving amoxicillin in cellulitis after a dog bite? You might have heard of that. Why not Keflex for those? It's because dogs' mouths are colonized with a gram-negative called Capnocytophaga that produces, you guessed it, a beta-lactamase. So we need something stronger, and we give amoxicillin in that case. So I could go on, but these are some of the more high-yield examples that I wanted to show you. Okay, that's it, that's all. Let's review that summary slide again. 1. Many bacteria, particularly gram-negatives, can have resistance to beta-lactams by producing beta-lactamase enzymes. 2. Amoxicillin clavulanate has a beta-lactamase inhibitor that extends its gram-negative coverage, including beta-lactamase producing organisms, such as E. coli, proteus, klebsiella, and many other enterobacteriaceae, your gut gram-negatives. The nasty anaerobes, Bacteroides, Fusobacterium, and Prevotella, Hemophilus influenza and Moraxella catarrhalis, which are respiratory tract gram-negatives, and Capnocytophaga, which we see in dog bites.